So I'm just going to give a quick little overview of the kind of the I don't know, the issues and Arctic hydrology and why it's different from, say, just normal hydrology, everyday temperate region hydrology. So and the main issue is in the cold regions, you get the soil pore water can freeze. That can be seasonally, depending on where you are, or if you're in the more northern climates, you can get permanently frozen soil, which is called permafrost. And on that terrible picture, you can kind of see areas of that dark black line, which to me doesn't really seem to cover the whole region. It's kind of where you can get freezing soils, although that picture is so old, it may not be up to date anymore because that line is moving to the north. And so what happens is, in a seasonal sense, if you look at that, we have winter, spring, and then summer, and there's a lot of things in there, but I think the main thing is that temperature profile line. As in the winter time, you basically have the frozen temperature kind of all throughout the soil. If you're in an area where it freezes in the spring, you're still frozen down at the deeper levels, but you have started to thaw out in the upper levels, and you're kind of approaching unfrozen soil at the top. And then in the summer, you have a profile that you're still frozen down at permafrost, obviously, if you have some. But then all above that, you might be unfrozen, and then it's quite warm at the summer. And then this cycles through year after year, and the lines would look a little different depending on from year to year, depending on how hot it was, or those sorts of things, or how much snow you had on the ground, because that affects things as well. We'll talk a little bit about that. But that's kind of the general scheme that you see. And so from a different look at things, if the horizontal axis is the ground temperature, to the left is negative and to the right is positive, and then it's depth. And this is two different sites in near Fairbanks, Alaska. And basically what it's showing is that, you get like this cone of thaw. And so that one on the right really kind of shows it well. So in the winter, it's kind of frozen mostly throughout, but in the summer, it's frozen, still frozen down at the bottom, but it's warm at the top, and so you can kind of get you see these kind of pothole lakes in Arctic regions, and those are caused by this phenomenon a lot of times. If we look at the soil temperature, the seasonal soil temperature, so this is the same two sites, and the temperature is on the vertical axis, and time, it's basically one year of temperature plot, and it's at different depths from the surface down to 40 centimeters. And what you see is that in the wintertime, for both of them, it's pretty much the same. You see the same kind of pattern. All the soils are frozen, even down at 40 centimeters. But then as spring comes, starts to warm up, eventually thaws out around it's like May or June, and then the different depths matter more. So the surface gets quite warm, up to maybe like 15 degrees, 10, 15 degrees, and then the deeper depths are still kind of froze, kind of mimicking that picture we saw earlier. And then as the fall comes on in the winter, then it starts to cool off, and then not only do the temperatures go down, they start to go down more uniformly. And so where you really see the variability is in the summertime, and that's where you kind of get in that freeze thaw cycle. And if you get deep enough, depending on, kind of where you are, that'll be a deeper spot in warmer areas than in colder areas, where it's just pretty much stays the same temperature all the time. So, that's temperature and soils, but this is about hydrology. So, how does that affect our hydrology? So in frozen soil, either seasonally or in permafrost, that's going to significantly affect the hydrology in the affected regions. So the frozen soils reduce infiltration due to the reduction in the porosity, especially in permafrost. So if the soil is wet and it freezes, then the number of holes, you have in that, and then and really the number of pathways you have to that soil is really going to go down. And so that's going to be represented as also a reduction in the hydraulic conductivity. So the porosity is kind of just taking up the space, and then the hydraulic conductivity, you're blocking the pathways. So then frozen soils also alter the movement of groundwater, so that's going to reduce the depth of the transmissive zone. So if you had the groundwater, say it just was free surface and went all the way to the land surface, wherever it's froze, that's no longer going to flow horizontally to any real extent. Also, you're going to impede your recharge to your groundwater, and so you're not going to have the recharge occurring. It's also going to impede daylighting. Daylighting is I guess a fancy term for the surfacing of the groundwater. So if the groundwater is pressurized, it would daylight and form a stream, seep. But if the ground's frozen, then it can't do it. And so it has a lot of different effects on your hydrology, depending on what kind of hydrology you have. And so the hydraulic conductivity will decrease as the soil temperature drops. And the response to the soil depends on the soil properties of the texture, the thermal conductivity, the thermal capacity, the moisture content, and then your kind of unimpeded infiltration rate. And then there's a few different soils on the right-hand side, kind of different, showing you the different textures and kind of how the hydraulic conductivity varies. On the vertical axis is hydraulic conductivity, and that's basically orders of magnitude, because it changes a lot based on the moisture and the temperature both. So it's really like a 3D kind of figure would be better. But it does show you how the different soils are affected by the temperature, and you can see that it's orders of magnitude and different as the soils become completely frozen. So normally the soil hydraulic conductivity depends on the soil moisture and the soil properties, like I was saying. But as the soil freezes, the ice content becomes additional consideration. And since ice in the soil column is essentially impenetrable, and as the ice content increases, then the soils become less permeable. Picture of Aaron over my critical slide area. So you can see this is a fraction of liquid water as the temperature changes. And at zero or right above zero, then we're going to have 1. And then in the soil, you don't just get like 100% frozen it's not like turning a switch on and off. There's a curve that corresponds with the temperature. And then the hydraulic conductivity also varies with the temperature as well. And so as you got this kind of frozen condition, then this is the corresponding change in the hydraulic conductivity, and it's going down. And again, these are orders of magnitude, each one of these lines. It's not like, this is not a linear graph. It's a logarithmic graph. Stuck in the wrong spot. So infiltration rate, it depends on your saturated frozen soil. There's 4 different graphs. Sorry. So there's 4 different graphs. So if you have A, which is the line at the bottom, if you have a saturated frozen soil, you have a infiltration rate that's just, it's never going to change because it's saturated, and so you've reached the saturation infiltration rate. And if it's frozen, then it's basically zero. There's no there's no water. So in the curve B, you have, if you had the same exact thing, but the soil was thawing out over time, you would see the infiltration rate rise for that soil. C would be that kind of normal curve you would see if you had no frozen factor. So infiltration rates are high in the beginning, but as because you got the suction of the dry soil pulling the wetting front suction down, but as you reach kind of saturated conditions over enough depth, you get saturated hydraulic conductivity infiltration rate. So it approaches a value asymptotically. And then the last one is the water freezing as it enters the soil, D. And so, you know, that curve's just going to more rapidly drop down, and then the kind of the plateau is no longer the hydraulic conductivity, saturated hydraulic conductivity. Now it's zero, because once it's completely froze, it's going to stop transmitting water. So how do we get rid of Aaron's picture? Oh, there he goes. Bye, Aaron. So how do we simulate the frozen soil in GSSHA? So we look at the snow cover. We have a model called the continuous frozen ground index model that accounts for the soil being froze based on the counting of temperature. And then we can make adjustments to the soil property based on the soil skin temperature, which is the temperature that we have available in GSSHA doing any kind of long-term simulation. If we're running GSSHA with a GIPL model, which Noel's going to talk more about, we'll have a soil temperature profile. And so then we have effects of soil properties along a profile, and not just a simplistic model. Keep this going. So there's several different kind of levels of complexity, I guess, that you can use. And so the simplest one is just to say, well, if there's snow, it must be cold. So therefore there's no infiltration. And so I'm going to say the word card a lot. And what card, there's a file called a project control file, and you put little cards in there that have these keywords, and this one's like snow, no infiltrate. So in your project file. So that's all you have to do. You add that card anywhere there's snow, then it's not going to infiltrate. That's a very simplistic. So to move up in complexity, there's a model called the continuous frozen ground index model. So it's based on an hourly summation of below freezing temperatures. So that's computed in each of those computational cells that Aaron was talking about. And so you set a threshold for frozen soil. So if it's below the threshold, it's not frozen. If it's above the threshold, it is frozen. And so if it's frozen, then the infiltration ceases in that cell. And although this is a pretty simple tool, it does account for some important things that we know affect the soil, which is the snow cover and the feedback from the ground. So originally, this method came up by a couple of guys. They applied it daily, and it was basically for an entire watershed. We're looking at a cell-by-cell basis, and we found we got better results if we did hourly instead of daily temperature. There's the formulation, and the CFGI, that's continuous frozen ground index. It's index in degrees, negative degree days. So you're kind of adding up the days below zero. and then when you hit a threshold, you'll freeze the ground. So it accounts for degradation to the ground, which is important. T is the air temperature, so it's based on the air temperature divided by 24 because it's an updated hourly. So we've modified the original equation that's been used. K is a factor related to the insulating effect of the snow, and the default is 0.5. And then D is the depth of snow in the cell. The parameters, so to use the model, you put the card, there's the word card again, CFGI in the index in the project file. And the soil is assumed to be frozen once the CFGI hits the threshold value. The default value is 83. That was from the original paper. And I think that was up in the Northwest United States. So is 83 a good value everywhere? I have no idea. The results are sensitive to that value, obviously, because once you hit that threshold, your ground is frozen. And so, if you're going to use this method, you probably would want to calibrate that factor. If you want to vary that value, you just put another card in there. It just says CFGI index, followed by the value you'd like to have. If you want to freeze, later, then you'd put higher value. If you want to freeze earlier, you put a lower value. And then the snow index value can be changed by including the card CFGI _K in your project file. And the default is 0.5, like I said. So if you increase that K, you increase the effect of snow in insulating the soil. And I'm not an expert on snow, so I don't know how you would decide that other than just to calibrate the thing. That's simply for the methods we talked about so far. You just say, well, the ground's froze, therefore the infiltration is 0, and that's fairly simplistic. However, if the ground froze, the infiltration is going to be quite low, so it's not a terrible assumption. We have another option in there that says, well, if the ground is quote unquote froze, then use this equation to compute your hydraulic conductivity based on the temperature. So where the K sub T is the effective hydraulic conductivity counting for the temperature. T is the temperature in Kelvin. KT sub theta is the actual hydraulic conductivity for the soil based on the water content. I think we discussed how the hydraulic conductivity drops with lower water content. K sub F is the hydraulic conductivity of the ice, which is a set value 0.0036 centimeters per hour, which is 0. SE is the relative fraction of the liquid content. And that is computed from the temperature and then the amount of energy it takes to change from ice to liquid or from liquid to ice. And G is the gravity. BP is the soil bubbling pressure. And then the lambda is the Brooks and Corey soil distribution index. Those last two things you can pull from the GSSHA wiki for your different soils. So it looks complicated. It is, but you don't have to really do anything. It's just, you just turn it on. So going back over that, so if you want to use that instead of just a default, which there's no reason not to use it because it doesn't really require you to do anything. Just add that card saying you want to use the equation instead of the 0. And it'll work with any green and apt infiltration model. Is not fully verified. It's something that we got from some other researchers at the University of Alaska Fairbanks. If you use the GSSHA GIPL method, to adjust the soil hydraulic conductivity of the soil. Then this is used. So if you're using the full thermal soil profile in each cell, like Noah is going to talk about, then it automatically uses this method to compute the hydraulic conductivity. And unless we're using the GIPL, then the soil skin temperature is used for the soil or the ground temperature. So anytime you're doing long-term simulation, which you have to be doing this because you need the hourly values of hydrometeorological variables, especially temperature, of course. You get computations for evapotranspiration, and one of the things that you have to compute to do evapotranspiration is soil skin temperature, and that is literally means the skin temperature, the very top of the soil temperature. For cold condition, it's probably pretty good. If it was hot, it would be bad because that temperature can get, if you've ever had to like walk across a parking lot with your bare feet in August in Mississippi, that skin temperature can get extraordinarily high. That doesn't really represent the soil temperature in general. So the soil skin temperature is computed using this equation that I'm not going to talk about. It's just a standard equation that's used, and that's used in GSSHA. So after we've run our snow model, then we'll have you run with some of these different conditions, and then look at the different hydrographs in a spreadsheet. Hopefully, we distributed. So some things that we were, thinking about. I wouldn't say this is current. It might have been current last time I talked about this. Was the frozen ground is only dependent on elevation via the air temperature and snow depth. Land cover and soil moisture are not considered, and it's difficult to validate with field measurements. So we've played around with the idea of including some other things like shading, aspect, and snow cover, but we've never actually pushed that far enough to where it's been an in-release version of GSSHA. So that's it. Any questions about that before we talk about snow? I can't see if there. I can't see the chat. Is there anything in the chat, Aaron?
Nope.
Okay.
Rosie's typing something, but not yet.
All right. Well, I'll get this other one up. If we get a question through, we'll talk about it next.
Here's a question from Rosie. What sort of data sets do you need to run these different applications? What if you don't have any observed measured numbers?
You can get the hydrometeorological inputs that you need from any airport, no matter how tiny it is. And so there's NCDC data sets. It's called 3280, or at least it used to be. And you can get anywhere there's a airport, they'll have the data that you need to input it. And that's really all you need is the temperature data. And if it's not close, you still think, well, it may not be perfect, but it's probably better than ignoring the fact that the ground's probably frozen, because it would basically be telling you that the model, or any model, would be telling you that there's going to be a lot of infiltration when there is none. So ideally your measurements are as close as possible, but it is what it is. Anything else, Aaron?
That's it.
Okay.